think it's Durham University. Go to the page on University of Durham. And so Chris is an expert on anti-rate binaries and active galactic nuclei, and that's what she's going to talk about. She did her undergraduate at St. Andrews, next to the golf course, and then
before Prince William was there.
Oh, too bad. And then she did her graduate work at Cambridge, working with Andy Fabian. And then after that, she did a postdoc at Goddard Space Flight Center, and then another one at the University of Leicester. And then she started as faculty at Durham, where she's been for many years, and tell us about these black hole binaries and active galactic nuclei.
So Durham is a World Heritage Site. If you haven't been there, do come. It's beautiful. It's further north than you would expect. But what we're going to talk about is black hole accretion flows. Because the nice thing about black hole accretion flows is they turn black holes from looking for a black hole on a black background, which is not the most useful thing you can do, to looking at an intensely bright accretion flow, lighting up these regions of really strongly curved space-time around the black hole. So if we can understand accretion, if we can understand the accretion flow itself, then we can get observational constraints on strong gravity. So that's one motivation for wanting to understand accretion. Another motivation for wanting to understand accretion is that we can use the accretion flow to try and understand something about the relativistic jets we see from these sources as well. So what we can do is we can look at black hole binaries, and we can look at black holes in two kind of mass flavors. You can go for black hole binaries, which have been called quasars for the impatient because they vary on useful timescales like days, weeks, months. Even my attention span can get through a couple of days. And they give us an observational template of how these accretion flows respond to a varying mass accretion rate. And so we can watch the mass accretion rate onto the black hole change, we can watch the accretion flow change, and we can watch the change in the radio jet as well. So we can use the black hole binaries to build a working physical model of accretion flows. Once we have that, we can then kind of scale it up to the other mass scale of black holes we have, the ones that are supermassive black holes in the centers of galaxies. And we can use this scaled up model and compare it to what we see in active galaxies to understand which bits of physics do scale and which bits don't. And yet more motivation for trying to understand accretion and the associated jet is because we now know that we need to understand the energy feedback from the accreting supermassive black hole in order to understand galaxy formation. We know that the mass of the black hole in the centers of galaxies is somehow linked to the growth of stars in the galaxy as a whole, and that points to some feedback mechanism between the accreting black hole and large-scale structure. To understand large-scale structure in the universe, we need to understand the accretion flow and its associated jet. So let's start by looking at the black hole binaries. So we've got a 10 solar mass black hole and a companion star that's overflowing its Roche lobe and pouring material into an accretion disk that's accreting onto the black hole. And that accretion flow can be very bright. It's also normally very variable. Accretion disks around black holes are generically transient. So what you see are dramatic outbursts followed by slower decline. And so the mass accretion rate onto the black hole is changing by 6 orders of magnitude during this process, and that means we can watch a huge range of mass accretion rates onto the same black hole. But also, since they're all about 10 solar masses, we don't have to just look at one black hole. We can stack them all together and try and get some idea generically of their behavior. So these are light curves that go over 2 years, and you can see there's this dramatic variability. And so we can use this as a template to try and understand what's happening accretion flow. So, what do we expect the accretion flow to be doing? Well, the sort of models of accretion disks that we've had for 30 years, the Shapiro-Sunyaev disks, they make some very clear predictions. So the idea is you've got differential Keplerian rotation, so the material that's closer in is trying to move faster than material further out. And so they kind of slide across each other, these rings, and there's friction. And that friction dissipates heat, which then, if this material is optically thick, gets radiated as a black body. It's much more complex than just friction. It's actually some evil magneto-hydrodynamic dynamo, but let's not go there for the moment. So, what we've got, a large radii. We don't have that much gravitational potential energy, but we've got a lot of area to dissipate it over. So if it's roughly thermalizing to a black body, we expect small luminosity, large area. That gives us a lowish temperature from the outer disk. As we crawl inwards, we've got more gravitational potential energy and less area to dissipate it on, and so the temperature goes higher. Crawl in further still, we've got more energy, even less area, the temperature goes higher still. Now, if we have a solid surface, if we have a star, white dwarf, neutron star, whatever, then that would set this inner radius. But for a black hole, the inner radius is set by something slightly different, which is the innermost stable circular orbit you can have in Einstein's gravity. So it's a prediction of general relativity that you can only have stable circular orbits, and a disk is basically a collection of stable circular orbits. You can only have stable circular orbits down to some minimum radius. It's quite close to the event horizon, but it's not the event horizon. And at this point, you can't orbit stably anymore, and you spiral very quickly into the black hole. So that's what sets the inner radius in these kind of theoretical disk models. And that inner radius depends on black hole spin. So if you have a low spin black hole, then that last stable radius is larger than if your black hole is spinning in the same direction as your accretion flow. You can get closer in before it goes wrong. So that's what we expect to see. Now let's go and look at some spectra and see what we do see. So we're expecting, in these kind of simple disk models, that on a UFU spectrum, we'd have something that looks like this quasi-thermal sum of black bodies. So let's go and look at some spectra. This is 4 different spectra from one black hole binary. This is on different days. And you look at that and you think, that's not what those simple models predicted. There's obviously something much more complicated going on here. Yes, but let's accentuate the positive. If I look at the spectra that I've picked out in red, then actually they don't look that dissimilar from those very simple disk models we had on the previous page. So especially this one in red, it's a pretty good disk. Yes, there is a little bit of a tail at high energies, but the energy output of this accretion flow, it really does look like it's thermalizing to some sort of accretion disk structure, very similar to the predictions of those Shapiro-Sunyaev disks. Even this one down here, it's obviously dominated by a disk. Yeah, there's a bit more of a hard tail, but it's only 10% of the emission. We can sweep 10% of the emission under the table. We don't really care. The other 2 types of spectra that I've got on here don't really look like a disk. On a good day, at least this green spectrum seems to know something about the characteristic energy a disk should have, but obviously the emission's been broadened out into this high energy type. Even at my most optimistic, there's not much I can say about this blue type of spectrum. It looks nothing like this. So when you're confronted by this much complexity, and not helped by the nomenclature there's a very confusing set of names for all these different spectral states. When you're confronted with something like that, the initial reaction is to run away, far too complex. But instead, what I'm going to do is I'm going to throw away anything that looks too complicated. So I'm now only going to keep spectra that look like a disk. So if I throw away anything complicated, then I'm left with a series of spectra that look like a disk. Okay, that's good news. Where do we see these spectra that look like a disk? We tend to see them at the highest luminosities. So although the luminosity is varying, these are color-coded, so things in red are things that look like a disk. Things in blue are things that look nothing like a disk. And you can see that in general, you see those spectra that look very complicated, that look nothing like a disk at low luminosities, whereas at high luminosities, you're seeing things that look more like a disk. So here's a sequence of spectra that look like a disk from a single black hole binary. So you can fit disk models to them because they look like a disk. And when you do that, you're left with two numbers, one of which is the luminosity in this disk component, and the other is this maximum temperature. And that maximum temperature should be telling you about the inner radius. And if that inner radius, which is set in the emitting area, if that inner radius stays constant, then the luminosity that we see should vary with the fourth power of temperature, because these are kind of quasi-black bodies. So if you take the data and you plot the luminosity versus the temperature, both of which are observed quantities, then you get this set of data here, picked out in red and black. There's obviously more than 6 points here. I've just taken 6 points for clarity. Now, we don't know the distance or the inclination or the mass of the black hole to any sort of absolute precision, and so these cyan error bars are showing you something about the systematic errors that we have in converting to luminosity and Eddington luminosity. But having said that, that's a systematic. It can only shift you up and down. This characteristic luminosity t to the fourth won't change. This line is what you get if the temperature is changing, if the luminosity is changing as the fourth power of temperature. And the key thing that that does is it tells you that despite this large change in luminosity, there is a fixed emission radius, a fixed emitting area in the system, which is what I plotted here. This is the inner radius in fairly arbitrary units. It is constant, despite over an order of magnitude change in luminosity. This is really good observational evidence that there is a constant inner disk size scale, and that inner disk size scale is exactly what's predicted by Einstein's general relativity. It's not quite as simple as all this. You need to fold in some corrections. I'm not going to tell you what spin this is, because we don't know distances, massive inclinations to that great accuracy. The thing I want you to take home from this is there is a fixed size scale to the radius, to the inner radius of the accretion disk around the black hole. And that's exactly what is predicted by Einstein's general relativity. Okay, so what we've seen is that on long time scales, as the mass accretion rate varies over days, weeks, months, that spectra that look like a disk also vary like a disk. They pick out this luminosity t to the fourth relationship. Now I'm going to look at very short time scales. So on a couple of minutes time scales, what does the disk do if I look at it on a couple of minutes time scales? So here's its spectrum, and I picked out a very disk-dominated spectrum. And now, instead of looking at its spectrum as a function of energy, I'm going to look at its light curve. So here is 100 seconds worth of the light curve, and it does absolutely nothing. And this is exactly exactly what you expect. If you have a geometrically thin, fairly cool disk, which is what the Shikura-Sunyaev models do, then the viscous timescale on which you can change the mass accretion rate through that disk is quite long. It's of order more like an hour than a couple of minutes. So on these sorts of very short timescales, you don't expect to see mass accretion rate changes through the disk, and indeed, you don't. It's not varying at all. So, its spectrum looks like you expect from these Shikura-Sunyaev disk models. Its variability on long timescales looks like you expect from Shikura-Sunyaev disk models. And its variability on short timescales looks like what you expect from Shikura-Sunyaev disk models. It's a disk. Good, we've understood something about the accretion flow. So now it's time to bring back the rest of the data. And in particular, let's look at this very different type of spectrum that we threw away last time. So these spectra picked out in red were the ones that looked like a disk. This spectrum picked out in blue, you can see that on the new FU plot, where a peak shows you the characteristic energy at which the luminosity output peaks, you can see that this very different type of spectrum, called a low hard state, it's peaking at energies that are about 2 orders of magnitude higher than you would expect for any sort of Shikura-Sunyaev disk. It really doesn't look like a disk at all. It doesn't vary like a disk either. This is one of these low hard state spectra. If it was a disk, you'd expect it to be peaking here. It's peaking 2 orders of magnitude higher in energy. Even astronomers shouldn't be out by 2 orders of magnitude. And here is 100 seconds worth of its light curve. And I've normalized it to the mean, so that a factor of 2 high is here, a factor of 2 low is here. This is just 100 seconds worth of data, and you can see there's enormous variability on very short timescales. Compare it to the one we just looked at. See the spectrum change, see the variability change. I had normalized this to the mean as well. This is a factor 2 high, a factor 2 low, so that these curves are directly comparable. And you can see just how much has changed. Ultimately, the luminosity comes from mass accretion. So if you're able to vary mass accretion rate this fast, we can't possibly be looking at a geometrically thin disk anymore. The only way you can vary mass accretion rate fast is if your flow is very hot, where the viscous timescale can be much shorter. And if it's hot, it's got a large scale height. So we have to be looking at a large scale height flow in order to get this sort of variability out of changes in mass accretion rate. So that brings us very nicely to the other solution of the accretion flow equations. So over the last 10, 20 years, it's been increasingly realized that the Shikura-Sunyaev disk is not the only solution of the accretion flow equations. The Shikura-Sunyaev disk assumes that the plasma kind of thermalizes, which doesn't have to be true if we're dealing with a low density flow. If we've got a low density flow, then it doesn't need to thermalize, doesn't have to cool very efficiently. If it doesn't cool very efficiently, then it stays quite hot. And this whole new set of accretion flows, they were worked out quite a long time ago, but some of the key physics was put in by Narayan and Yi, these advection-dominated accretion flows. But these are just analytic approximations to probably a much more complex reality. We know that this process of allowing material to accrete onto the black hole, we have to lose angular momentum to enable the material to fall in. And the way we do that is via this complex magnetic dynamo. So in this hot, geometrically thick flow, there have to be tangled magnetic fields as well. So, whatever its properties, we'll just kind of use generically this kind of idea that there's a hot, optically thin, geometrically thick solution of the accretion flow equations. And if that's true, then it's hot. So we can Compton scatter any kind of seed photons. We don't want too many seed photons because Compton scattering sucks energy from the electrons. And if we take too much energy, if we cool the flow too efficiently, it will come back down and form a thin disk. So in order to put the disk all the way underneath it, we have to bring the disk a long way out so that we don't cool the flow too much. So the sort of geometry you're left with is that you have some sort of hot, geometrically thick, but optically thin flow that replaces the inner disk. And then you can get very nicely the sorts of hard spectra that you see in this very different state.
Question.
Yes?
What's being done to compare the cutoff energy hard state against between different sources? I know that there's this effort to get the multicolored, this black body,
Yeah.
and return spin patterns and so on.
Yeah.
Has there been any parallel effort to correlate with the high cutoff?
You mean this temperature? Yes. In fact, I'll show you some data in a minute. So let's watch this transition. So hopefully I've convinced you that at high mass accretion rates, we've got a disk down to the last stable orbit. At low mass accretion rates, we can get these sort of strange spectra and rapid variability that we see, if instead we replace the inner disk by one of these hot, fluffy flows. So the only way to get from here to here is to move the disk in. As we move the disk in, we would expect to see the disk spectrum get more and more important, and we'd also expect that we cool this hot flow more and more. And so if you Compton cool this hot flow, you would expect that the spectral index will go from something like this to something like this. You expect to see it soften as the temperature goes down. So let's go watch one of these transitions. Here we go, the spectra are on the left. We're pushing. So according to these models, we're pushing the disk in. So we expect the disk to get more important, but we're also cooling down the hot flow more. So we expect this tail to get steeper because the electron temperature is getting lower. And you can see the electron temperature getting lower. Not wondrously well from these data, but I've got a little stash of Cygnus X1 data on my disk as well. And there you can see it much more clearly. So,
New star be able to do this?
New star doesn't go high enough out. Remember with Cygnus X1, background isn't so much of a problem because it's really bright.
The new star is like 60.
New star's 60, so it'll take you only to here.
Yeah.
But it'll do fabulous things for active galaxies. And I mentioned at the start about the jets. So we know we see radio emissions, his work especially done by Rob Fendler and his collaborators. And what they see is that if you take the X-ray flux that we're seeing from this hot fluffy flow, and you take the radio flux that's telling us something about the jet that we see in these sources, then these two know about each other. That as the accretion flow gets brighter, then the jet also gets brighter. But as you up the mass accretion rate through that hot, fluffy flow, eventually it becomes so dense that it starts to cool more efficiently and collapses down to this alternative Shikura-Sunyaev disk. So when you make that spectral transition, when you go from having one of these hot, fluffy flows replacing the inner disk to where the flow has become so dense that it cools and collapses to form the inner disk, that's the point at which the jet luminosity also collapses. So we can do that. Any large-scale height flow, remember it's got large-scale height magnetic field entangled in with it. More or less the only thing that theorists agree on in terms of launching jets is that you need large-scale height vertical magnetic field somewhere close down to the horizon. So when we've got one of these large-scale height flows, we also have large-scale height field, and that gives us the jet. So then what we can do is, as we push the disk in, this is just an animation of what I was showing you. As we push the disk in, we get more disk photons, but we're also cooling the flow, and so its temperature is going down, so the spectrum is getting steeper. But when the disk replaces the hot flow, there's no more large-scale height flow left. No large-scale height flow, no large-scale height magnetic field, no large-scale magnetic field, no jets. So these sorts of models give you a way to tie together the spectral evolution that we see with these quite dramatic spectral transitions with the behavior of the radio jet. So they've got quite a lot going for them. But let's explore them in a bit more detail. I went quite swiftly over the fact that we can get rapid X-ray variability from these flows. Let's look at the characteristics of that variability in more detail. So when it looks like a disk, it behaves like a disk, and we don't get much rapid variability from it. But when we've got one of these very different types of accretion flow, we see lots of X-ray variability. So let's look at the characteristics of that X-ray variability that we see from the flows. And the way to look at variability, to see how much variability power we have on each timescale, is to do a power spectrum. And again, what I'm plotting here is power times frequency, in much the same way that I plotted nu FU for Spectra, because then a peak in power times frequency tells you the typical timescales on which the variability power peaks. And you can see this very intuitively from scaling the light curve over different timescales. This is a view graph I stole from Philip because I think it's just such a visual way to show what power spectra are showing us. So if I take a very short 1/100th of a second worth of Cygnus X1 light curve, and I normalize it to its mean value, I can see that there's not much variability going on these very short timescales, which are the very highest frequencies. If instead I took 1/10th of a second worth of data from Cygnus X1 and scaled it to the mean, you can see that there's much more variability here. So we're now talking of these sorts of frequencies here. And it's rising, we're getting more power. There's even more power if I do 1 second worth of data from Cygnus X1. So I'm now up on these kind of time scales. And then when I go to even longer time scales, it starts to come down again. And what you're seeing is that we're rolling over the side here. And so typically what you see from these black hole binaries in this low hard state is you see this band limited noise. There's a range of timescales over which that variability power peaks. And we're typically talking something like 10 seconds to 1/10th of a second. Okay, so armed with that, let's go and look at, for each of the spectra I showed you in the transitions, let's look at the variability power spectra associated with each spectrum. So here's the first one, and here's its variability power spectrum. And the first thing you see is that, actually, okay, there is this broadband noise in here, but there's also a very clear characteristic timescale that's picked out by the data. This thing. It's called a quasi-periodic oscillation, because it's not completely periodic. If you look at it, you can see it's not a spike, it's got some width to it. And that's clearly picking out some characteristic timescale in the variability. Okay, so let's now watch what happens as we make this spectral transition. We've already seen what happens to the spectra. Now let's watch and see what happens to the variability. So here's this very characteristic timescale. It's roughly 3 seconds that it's picking out in these particular data. Now let's move into the transition and see what happens. The most obvious thing you just saw was that characteristic timescale swept across from about 3 seconds to something more like 0.3 seconds. It's clearly gone to much shorter timescales. And that's interesting because if you look at this picture, it's showing you that there is a characteristic radius in this system, and that characteristic radius is getting smaller, and so any timescale associated with that characteristic radius is going to get faster, which already gives you a kind of qualitative way to think about this characteristic timescale we're seeing in the system. And that's really important because these models, they're called the truncated disk models, they were kind of put together to explain the spectral changes. So the fact that they can explain the spectral changes perhaps isn't that surprising. They were designed to explain what you just saw happen in the spectrum. They were not designed to explain what you just saw happen in the variability. And yet they already give us at least a flavor or a framework with which to think about this variability. That's quite nice. So let's ask the most obvious question. The most obvious question is, what is this characteristic timescale? I've got a characteristic radius here. The most obvious thing you can think of is Keplerian. We know that in these spectral transitions, we need to end up at more or less the last stable orbit, and we might have moved by a factor 10. So we should be picking out radii from, say, 5 to 50 gravitational radii. We know we see this QPO frequency move from something like 0.1 to 10 hertz. That's 10 seconds to 0.1 of a second. Keplerian frequencies are here. They are way too fast. Whatever this is, it's not Keplerian. Right, what else can we think of? Well, this is a black hole. It's probably spinning to some extent. You can't imagine a really a Schwarzschild black hole, and as long as you're spinning low, moderate, high, then you'll drag space-time around with you, and that means that your gravitational potential is not spherically symmetric anymore. You have frame dragging. And so if you perturb, say, the inner edge of this truncated disk, if you perturb it vertically, it's trying to go around the black hole like this, but the space-time itself is spinning around. So it gets dragged around, and it does this, and precesses, like this picture. What about that time scale? Now, this was done by Stella and Vietri quite a long time ago now. They said, hey, what about lens theory or nodal precession? And so let's put that on the same diagram. Now it depends on black hole spin, of course. So this is done for low spin. This is 0.3, 0.5, 0.7, 0.9, and maximal. And so we're picking out a single radius, and ooh, look at that. It's gone straight through the area we wanted it to go in. That's pretty good. Yeah, I mean, you could get picky and say, well, when we get towards the last stable orbit, these frequencies do go higher, even for quite moderate spins. These lens steering frequencies go higher than anything we've ever seen from black hole binaries, from this QPO in black hole binaries. But in fact, the real sticking point for these models is that we can look at the data and we can say, well, what is the spectrum associated with that quasi-periodic oscillation? If we were perturbing the edge of the disk, what you might expect is that you were seeing different angles to the hottest part of the disk emission. So you might expect that this QPO signal was mostly in the hottest part of the disk emission. It is absolutely not. It's been known for many years. Let's take a close to the transition one here, where you have a very strong disk and a fairly cool Compton tail. What is the spectrum of that quasi-periodic oscillation? It looks everything like this tail and nothing like this disk. And so some people kind of drifted away from these models. But all that's telling us is that we don't really want to do lens steering precession of the disk. What about doing lens steering precession of the entire hot flow? Because, in fact, we wouldn't do lens steering precession of a thin disk. A thin disk, if it's misaligned from the black hole spin, will simply give you a stable walk. In order to make it precess around, you've actually got to do something a little more like a hot flow. Because in a hot flow, it's hot. So the sound speed is fast. And the torques are carried by waves. The torques from a misaligned flow and black hole spin are carried by waves, and they need to get across the whole flow fast enough to drag the whole thing into global precession, even though it's still differentially rotating. Well, you look at that geometry and think, yeah, well, that would modulate the Comptonization emission for you and make the QPO, but can it really do that? So Christopher Gill does some of these, I call them heroic simulations, where they start off, he started off an accretion flow with a tangled magnetic field in it, and he set it off misaligned from the black hole spin. The black hole spin is vertical in this picture. And he sets it off, and it's about 50 Rg in radius, and the whole thing is globally precessing around the black hole. Yeah, I think these simulations are heroic, actually. So, the simulators say they can do it. And now we're not talking about a single radius anymore. We have to integrate, we have to do a sort of weighted average of the lens steering precession of all the radii in the hot flow. When you do that, your predicted QPO frequencies land so exactly in the box, it almost worries me, because I think maybe I fiddled it. But honestly, I didn't really fiddle it. They do just simply land straight in the box where the observations lie. So, yeah.
So the frequency, the precession frequency, it's not quite just the outer edge of that flow, but it's a little bit lower than that.
Yeah, you have to. It's higher than that, actually. So what you've got to do is you've got to do a mass-weighted average of all the radii that you have in your flow.
In your plot, it's just it's a way you say you get a mass-weighted average of the lens steering.
Yes. Yeah. And that puts you here. Right.
Well, it shouldn't be a Compton-weighted.
I'm sorry?
It shouldn't be a Compton-weighted average. Most of the mass will be in the outer parts, and most of the Compton wide panel will be in the inner parts.
Well, you've got to do two things.
But it's globally precise.
So firstly, you can take the mass distributions from the heroic simulations, and that's in fact what we do. So we take their surface density. So there will be some change in Comptonization across this. Obviously, you'd expect the inner regions to be brighter than the outer regions, but the precession frequency is set by the whole flow, rather than just the bit that's radiating.
You're claiming this really is a collective thing.
It's a collective thing that the bending waves that carry the torques from this aligned black hole travel fast enough across to drag the whole thing into global precession.
Well, his aspect ratio is
About 0.2.
0.2 and what range? It's hard to see from the top.
Yeah, yeah, it's a shape.
It looks, yeah, so it's extending in like cusp-like
Yes.
toward the center.
Yes. You started off with a torus and then just let it go and make a shape.
But the precession frequency is very strongly dependent on radius, right? So
Yes.
I'm surprised that those parts
when you're
were-
getting global precession. The theorists said this should work. So the theorists, who we didn't particularly believe, so people like Steve Mother who've done things with flows, they said that the condition for it to globally precess is that your viscosity is smaller than your scale height. Your scale height's telling you about, in some sense, the temperature, how fast the bending waves can go
Well, I
across,
think we
whereas viscosity nails you to the floor.
Yeah, I can believe that the outer factor of 2
Yeah.
in radius might, collectively
Yeah.
sense. But if you have something that extends over, say, a factor 5 or 10,
Yeah. Well, he's managing to get it going over a factor of about 8.
boy, it sounds.
Well, that's. Well, remember,
Yes,
we're not.
remember the precession frequency was like R minus 3, wasn't it?
Yeah, 3,
So-
no, 5 halves, isn't it? But
You
yeah.
just do the third part.
Yeah.
So, factor 5 and
Yeah.
that's a huge.
It's a huge
Much-
change, and you just, you need to really kind of yank it round. But that's
Yeah.
what the bending waves do. They keep it together.
But that's, I think, one of the key points is that it gets small, and that the bending waves can travel much faster than the precession time.
So more or less, you don't ever need it. You don't see this QPO when you think the radius might be more than a factor of 8 or 10 bigger than the inner radius. But what you also see more variability than that. Remember, we had this stochastic noise that sat underneath the QPO. And one of the things about this stochastic noise is it's got a timescale hardwired onto it as well. It's got this kind of low frequency break timescale hardwired onto it. And that low frequency break correlates very well with that QPO frequency. So if you plot the QPO frequency across the break frequency, they track each other extremely well. So this is saying that not only is there this characteristic timescale that the QPO is setting, but there's another characteristic timescale in the system as well, and that knows all about the timescale for this QPO. So, next question is, what's that? Well, one of the things that you just saw in these heroic simulations is that you've got tangled magnetic fields. And tangled magnetic fields, as the simulators have been telling us for quite a long time now, tangled magnetic fields in a large scale height flow give us large fluctuations in both space and time. This magnetic dynamo is a great source of stochastic noise. It's basically stirring up fluctuations at all radii on all time scales. So here's our hot fluffy flow, and there's the MRI, this magnetic dynamo that's stirring up fluctuations on all time scales, but you can only move mass through the flow on the local viscous time scale. So you can stir up lots of fluctuations, but the only ones that are going to propagate down through the flow are the ones that are slower than the local viscous time scale. In other words, when you're looking at the mass going through the flow, you're stirring up fluctuations in mass accretion rates at each radius at this characteristic viscous frequency. And at large radius, that viscous frequency is quite long, but as you come further in, it gets shorter and shorter and shorter. So you're stirring up fluctuations on shorter and shorter timescales as you go in. So you've got an inner radius and an outer radius. This whole thing is precessing to make you the QPO, And then the rest of the flow, just these stochastic fluctuations, are stirring up power, variability power, with a timescale that depends on radius. And then as your flow comes in, you're going to lose the largest radius bits of the flow, you're going to lose the lowest frequency noise components, and you're dealing with a smaller region, so your QPO gets faster. So this is just given a model in which you can get both the QPO frequency moving and this low frequency break tied to it.
Just to be clear, the reason you're saying that you don't get variability through the outer thin disk is this time scale is a lot longer than that.
Yes. Yes. Yes.
What's the proportionality between those two frequencies?
I'm sorry?
Can you produce a plot where you see the correlation between those two frequencies?
Yes.
What's the
Probably a factor of 10. So
Is that linearly?
Is it linear
or
to some power? Or
is it linear or to some power? Or is it just strictly linear?
it's just a power. But I can show you this in more detail by actually taking this model and fitting it to real variability power spectra. So the data points here are real variability power spectra, and the red line is a model. This is done predominantly by my student Adam Ingram. And what he's done is he's coded up this idea that you have a hot flow that's got an outer radius and an inner radius. And this is globally precessing, and that sets the QPO frequency.
As a harmonic too?
There's a harmonic too, but we're and then this outer radius, and you have to use the same outer radius, is where we're stirring up the longest timescale noise. And then as we go in towards the inner radius, and you have to use the same inner radius as you use for the QPO, is where we stir up the fastest noise.
It's still alpha as a free parameter, I guess.
Yes, we have viscosity in there as a free parameter. There are a few more free parameters, including things to fit the harmonics, because we can't do harmonics yet. But this is the first time anyone's fit a physical model to power spectra. And look what the outer radius is doing. This is the outer radius. We go into that transition, and we can still fit the power spectra, and we get down to somewhere a lot closer to the black hole. So, these truncated disk models, not only do they give you a nice spectral transition between these hot, fluffy flows and these disk-like spectra, they also give you the way to describe the spectral changes as you go into the transition, and they give you a way to describe the variability changes as you go into that transition. And you can do it with the same radii. You need the disk to be moving inwards, then you can give the spectral changes and the power spectral changes together in the way that describes the data. So it's a pretty good model. So now let's scale it up to active galaxies and see what we do and don't understand.
Before you go there, is there evidence that the jet processes on
No.
a similar timescale as this hot flow?
No, you couldn't, so you're talking
that's
about
still
timescales of 0.1 seconds
Right.
for this?
Right, so okay.
So it's just too fast.
So
But
that's still locked to the black hole,
Well,
or some average of
what
it.
Chris Vogel is wanting to do is he's wanting to do his heroic simulations and include the jet, so that he's able to see what happens as you come around. So it's an interesting question. Is the jet direction set by the black hole, or is the jet direction set by the accretion flow? And you can make some quantitative estimates that tell you that the jet spin should set it if it's spinning more than about 0.3, 0.5. But those are just kind of quantitative estimates, and it would be fabulous to see in these heroic simulations what actually happens. Well, what actually happens. What happens in a numerical simulation, which may not be the same thing as what happens in reality. But let's not go there. Let's go scale this up to AGN and see what works and what doesn't. So the most obvious thing we've got to change is the black hole mass. We've obviously got a bigger black hole mass in there, but how much bigger? And when I started in this field, and we're talking 20 years ago and a few more as well, then we had not a clue. Black hole mass could be somewhere between 10 to the 6, or 10 to the 8, or 10 to the 9, and that makes its accretion disk temperature very hard to pin down exactly. But one of the things you could generically say was, okay, we can scale the accretion disk temperature, and generically it should come out somewhere in the ultraviolet. So, rather than having a disk peaking in the soft X-rays, we've got a disk peaking in the ultraviolet instead. This is unfortunate because interstellar absorption means you can't see the ultraviolet. So, that's that. You can't then play games with looking at the peak of the disk emission. Okay, what else have we got? We've got a much broader spread in black hole masses. So one of the key things that's come out of active galaxies in the last 10 or 20 years is this realization that the AGN, the black hole at the center, knows something about the mass of its host galaxy. Big black holes live in big galaxies, little black holes live in little galaxies. And this is telling us something very deep about galaxy formation and about this feedback mechanism. But for here, all I'm going to do is use the fact that it tells us black hole mass. So we now actually have a way of roughly scaling black hole mass from either stellar velocity dispersion or broadline region width, some way of actually getting the mass of the black hole. Which means we can convert the luminosity we see to fraction of Eddington luminosity. And it's that should scale when we scale mass. So an accretion flow at 10% of Eddington onto a black hole should look pretty similar to an accretion flow at 10% of Eddington onto an active galaxy, apart from this fact that our disk temperature has gone down to the UV rather than the soft X-rays. So let's just see, okay, we've got some evidence that disks really do peak in the UV. If you look at UV spectra, this is co-added quasars, you can see there's a continuum, nice blue, disky like continuum under there, but it's nothing like so clean as the black hole binaries, because UV light is ionizing, so you get all these amazing lines that are excited by the UV flux, huge broad emission lines and blends of ion 2 everywhere, so it can be quite tricky to pick out the disk continuum under all these lines. And then, when you look at the line ratios, you just see this mess of, you thought black hole binary spectral states were a mess. Well, trust me, looking at optical AGN classifications, that's another mess. There's quasars, liners, Seyferts, that's not even counting radio galaxies in there. So let's try and make some sense of this, and let's start in the same way as we started with the black hole binaries, which is by throwing out anything complicated. We know that there's obscuration along the equatorial plane. Throw away anything that's obscured. Let's not go there. We've got enough problems even when we can see it directly. So let's now take only unobscured objects. So if we do that, we then only have unobscured objects, so we can't play with obscuration anymore. But we see this big range of luminosity. Quasars are obviously much brighter than Seyferts. Well, this is something you can do very easily. If you take an accretion flow at the same fraction of Eddington, but put it onto a larger black hole, a more massive black hole, you'll get more luminosity out, but your ionizing spectral shape will stay very similar. So you'll get the same line ratios. So this is the easy, obvious way to get from Seyferts to their higher luminosity cousins, the quasars. But what we've just learned about black hole binaries is that we have huge changes in the spectral energy distribution as a function of mass accretion rate. This is a single black hole, so its mass and spin have not changed. But in response to changing mass accretion rate, this is how its spectral energy distribution changed. And these are the sorts of pictures and the sorts of geometries we drew in those truncated disk ideas. So what happened happens to a single black hole at different mass accretion rates if we scale this up to an AGN. Well, all we've done is take our soft X-ray disk and made it a UV disk instead. We've kind of stretched it out. So, if AGN behave in the same way as black hole binaries, they should do this. Is there any evidence for that? Would be the first thing to ask. And the first kind of evidence you can think of is, well, there are lots of these different AGN classifications. If I change my ionizing spectrum so dramatically, I'll change my line ratios. And if you look at the sorts of different AGN classifications and you pick some that have similar masses, you can pick a set of AGN which go from liners to safe-at 1 quasars to narrow-line safe-at 1s that all have roughly the same mass but very different mass accretion rates. And so this makes you think, maybe these very different optical line ratios are just reflecting something about a very different ionizing spectrum. So let's get more quantitative about this. If I look at the X-rays here, and I say, what number would I have to multiply my X-ray luminosity by to get the volumetric luminosity? Obviously, in this blue spectrum, this hot, fluffy flow, my X-rays are giving me most of my volumetric luminosity. By contrast, if I look at this red spectrum here, my X-rays are a tiny fraction of my volumetric luminosity. I need to multiply this by a very large number to get my volumetric luminosity. And so Vasudevan and Fabian looked at a whole load of Swift spectra, because what you need in order to measure volumetric luminosity in AGN is you need optical and ultraviolet to get the disk and X-rays to get the tail. Whereas in black hole binaries, just looking in X-rays got you everything. So here you need optical and ultraviolet as well. So they did this and they tried to estimate volumetric luminosity, and this is that factor by which they had to multiply their X-ray luminosity to get the volumetric luminosity, and they're seeing quite a dramatic change. There's a factor 10 here, change in the fraction of the volumetric luminosity carried by the X-rays. So this looks very good. Let's go a bit further and actually look at the spectra that we're seeing. So this is a compilation by Martin Ward and his student Zhichuan Jin, and what they did was take optical and ultraviolet. This is SDSS with all the lines removed, and this is the optical monitor on XMM, which is simultaneous data with the soft X-rays and hard X-rays. And you can fit these data with disk models and a tail, but you always need this kind of component in the middle as well. It's not just a disk and a tail like I was showing you in the black hole binaries. There's this additional component in here. But in these low mass, high mass accretion rate AGN, that additional component is often called a soft X-ray excess, isn't really carrying most of the volumetric luminosity, which is very different when you get to standard quasars. So standard quasars, such as all the kind of Richards et al., Elvis et al. Spectral templates, they have spectra that look like this, where actually your volumetric luminosity is dominated by this funny component in the middle that we don't really understand. So it's called the soft X-ray excess. We might not understand it, but at least we can kind of measure it. And if you measure it, it's obviously got a kind of typical temperature on it. So you can measure that typical soft X-ray temperature in all of these spectra. Here it is. And you can plot that as a function of the accretion disk temperature. You might expect that it would know something about the accretion disk temperature. And it really doesn't. It's way too high to be the accretion disk itself, which is kind of obvious here. There's the disk down there, and here's our soft X-ray excess. It's generally way too high to be the disk itself, and it doesn't seem to correlate with anything. Well, I said it was way too high to be the disk, but some of actually the narrow line safer ones. And if you try and guesstimate where the disk should be in those objects, actually it starts to encroach into the soft X-ray region. Here's one of these where I've honed in on the X-ray region, and a pure disk that was around the 10 to the 6th solar mass black hole at Eddington. These are some of Shane's models with Variability. A pure disk obviously goes pretty much straight through the soft X-rays here. This is not an enormous soft X-ray excess. This is the accretion disk. And if we're dominated by the accretion disk, we can start to play those same games as we played in the disk-dominated black hole binaries. If we're dominated by the accretion disk, we can fit its spectra to accretion disk models and try and get black hole spin. Why not? Here's one that's completely dominated by the accretion disk. Here are the soft X-rays. A pure disk would have looked like this. There's a little bit in the hard tail that we don't understand, but most of it's in the disk. That's spin 0, that's maximum spin. It's really hard to get a maximally spinning black hole through this. You get quite a tight upper limit that this AGN is not spinning faster than A star with 0.6. Well, that was just a digression, and it's time to stop. Take-home message is that active galaxies do not have a standard spectral energy distribution. Their spectral energy distribution changes with mass accretion rate. At high mass accretion rate, you're dominated by the disk, but at lower mass accretion rates, the whole spectral energy distribution changes. Don't assume that there's a constant volumetric correction between the optical and the volumetric luminosity. Don't assume there's a constant volumetric correction between the X-rays and the luminosity. These things change.
A quick question about a couple slides ago. You were fitting a multicolored disk black body to optical
Yes.
UV spectra.
Yes.
And now in the A equals 0.998
Yeah.
curve, that's 2 orders of magnitude down from the spectral peak. So it's way, way out in radius.
Yeah, you
So-
can't get that through the data.
So, but hold on. If you were to say, okay, my physical model is 0.998, then what extent can you trust the emission in UV optical zone?
It looks like it is.
Well, but
And-
point being that reprocessing of some central continuum.
Reprocessing changes your spectral shape. It puts you on plateau. So this is something you see, especially in X-ray binaries, that if you take a few percent of your peak flux in X-ray binaries and reprocess it, you get yourself a nice little flat continuum out.
Okay, that might not be consistent with the hypothesis, but the point
So the
remains-
spectral shape is not consistent with reprocessing, is what I'm saying.
Well, it may not be, but still the issue remains that in this class of objects,
Yes.
the optical UV is far enough down on the
Yes.
on the black body tail
Well, you
that
say
you
that.
have to.
It's not. I mean, you have to take 10% of this and reprocess it in order to make an impact over here. In black hole binaries, because you're peaking here, you only need to take 1% and reprocess it and you're fine. But here you need a lot. You see, you need to
Maybe we
use...
should let Chris conclude, so
Mm.
then we can take more questions.
Right. So the SEDs change. Basically, bottom line, and they don't change quite like you'd expect from black hole binaries. So these, at very high mass accretion rates, my AGN look disk dominated. At the very lowest mass accretion rates, which are the liners, actually they look quite like these strange low hard states. For the ones in the middle, the bog standard quasars, every kind of Richards et al. SDSS quasar, the most kind of normal quasar you ever see, they look like these green and blue lines. And trust me, they don't look like any black hole binary spectral state I've ever seen. If I picked out this one, you might say, oh, isn't it kind of quite like this low hard state? Remember, this low hard state is radio loud and these are radio quiet. Something breaks. And so while you can make quite a good case for liners being like the hot, fluffy flows, and the narrow line safer ones like the disk-dominated states, your standard quasars just look kind of weird. So what's going on in these standard quasars? What can be breaking the symmetry between black hole binaries and active galaxies? And again, this is something Shane is working on at the moment. The idea, one of the obvious things that's changed is instead of having a disk in the soft X-rays, our disk emission is now peaking in the ultraviolet. Daniel Kroger's done some simulations, again, I think they're quite heroic, where he does a UV disk. UV bright disks power UV line-driven disk wings. You can't have UV line driving in black hole binaries because you don't have UV, you have soft X-rays. But in AGN, your disk power peaks in the ultraviolet. And so you can power a very strong wind. The mass loss in this wind will change the underlying disk structure. And maybe this is the way we break the scaling between the stellar and the supermassive black holes for our standard quasars. But that's just rampant speculation. Let's pull ourselves back to the data and do a quick summary. Basically, the take-home message, in black hole binaries, they're a great place to actually test general relativity because there we understand something about the accretion flow. When it looks like a disk, it varies like a disk. It tells us there's a last stable orbit in there, which is one of the key predictions of Einstein's general relativity. But then when you look at the spectral transitions, you can build models where that disk progressively recedes at lower luminosities, being replaced instead by a hot fluffy flow. And you can tie the variability properties both qualitatively and quantitatively into this picture as well. Then you scale it up to black hole binaries, then you scale up your black hole binaries to active galaxies, and you've got a very different spread in black hole masses, but these different black hole binary spectral states means you should also have very different ionizing spectra in AGN and different line ratios. We see lots of evidence that there are no such things as constant bolometric corrections from either optical or X-rays, just don't do it. But when we look at the spectra in detail, they don't quite correspond. We've got this very strange component that we don't understand called the soft X-ray excess. And that makes our life difficult. But it's difficult mainly in standard safers and quasars. In the liners, in the very low mass accretion rate guys, there's pretty much like the hot fluffy flows. In the narrow line safer ones, there's pretty much like the disk-dominated states in black hole binaries, and we can get spin. And maybe UV line-driven disk wings are changing what we see in the safers and quasars. Thank you.
We're a bit over time.
I'm sorry.
But maybe just one question. Quick question.
And I'm around this afternoon and a bit tomorrow morning as well if you want to come.
Well, so we will have cookies. So if those of you who have non-quick questions, you should take them upstairs. And Chris will be taking her to dinner, so if anybody wants to join us, please let me know. And as Chris just said, she'll be around tomorrow. And so let's thank her again.